You have made a decision today. Maybe it was small, what to eat, which way to walk, whether to watch this video or scroll past it. Now, here's a question that some of the world's best physicists take completely seriously. What if every decision you have ever made, every single one, actually happened? What if every time you made a choice, the universe split? And in the other version, the other choice happened too. What if right now, as you watch this, there is another version of you who scrolled past, who never saw this video, who is doing something completely different, and that version of you is just as real as you are? This is not science fiction. This is something that comes directly out of real physics. And today we are going to talk about the multiverse, the idea that our universe might not be the only one, that there might be other universes out there, lots of them, possibly infinitely many. And here is what makes this topic so strange. The idea of other universes does not come from one theory. It comes from 5 completely different areas of physics, all of them pointing toward the same answer from completely different directions. We are going to go through all 5. I'm going to keep it simple. I'm going to use normal words. And by the end of this video, you will understand what physicists actually mean when they talk about the multiverse and why so many of them think it might be real. Let us start. Type 1, the copy of you that already exists. Let me ask you something first. How big do you think the universe is? Our observable universe, the part we can actually see, is about 93 billion light years across. That sounds big, and it is. But here is the thing. That observable part is not the whole universe. It is just the part we can see from here right now. Think of it like this. Imagine you are standing in the middle of a huge flat field in the dark. You have a flashlight, the circle of light around you. That is your observable universe. Everything within reach of your light. But the field does not stop at the edge of your flashlight beam. It keeps going way beyond what you can see. The universe is like that. The part we can observe is just the part that light has had time to reach us from since the Big Bang. But the universe almost certainly continues beyond that. And the current evidence suggests it continues for a very, very long time. It might even be infinite. Now here's where it gets interesting. Matter can only be arranged in so many ways. Think about a bag of Lego bricks. You can build a lot of different things with them. But the number of different things you can build is not infinite. Eventually, if you kept building, you would repeat a design you had already made. The same logic applies to the universe. In any given region of space, a region the same size as our observable universe, there are only so many ways to arrange all the particles. The number is absolutely enormous, but it is a number, not infinity. So if the universe is infinite or just very, very large, something remarkable follows. At some point, far enough away, there must be another region of space where the particles are arranged in exactly the same way as they are here. Not similar. Exactly the same, which means there is another Earth with another you on it reading the same script right now. Not because of any weird quantum physics, not because of any exotic theory, just because in an infinite universe, everything that can happen eventually repeats. This is what scientists call the level 1 multiverse. And the scary thing is, it does not even require any new physics. It just requires the universe to be big enough, which the evidence suggests it is. You cannot visit this other version of you. The distance is too vast, so far that even traveling at the speed of light for the entire age of the universe would not get you close. But that does not mean they are not there. They are, and they are reading this sentence right now. Type 2, the universe that grew from nothing. Okay. Type 1 was already mind-bending enough, but it gets stranger. You probably know what the Big Bang is, about 13.8 billion years ago. The universe started extremely small and extremely hot, and it has been expanding and cooling ever since. That much is solid science. But there is something that happened right at the very beginning of the Big Bang that most people do not know about. Something called inflation. Right at the start, we are talking tiny fractions of a second after the beginning. The universe did not just expand normally. It expanded at an absolutely insane rate, way faster than normal. We are talking about the entire observable universe going from smaller than an atom to something the size of a grapefruit in a fraction of a second that is so short, no human unit of time can describe it. That is inflation, and it explains a lot of things we observe about the universe, why it looks the same in every direction, why it is so flat, why it does not contain certain exotic particles we would expect. Inflation solves all of those problems. But here's the part that leads to the multiverse. Inflation does not necessarily stop everywhere at once. Imagine blowing up a balloon. But the balloon has a small area on it that is made of slightly different rubber. That spot expands much faster than the rest. It bubbles out. It becomes its own separate section. That is kind of what happens in what physicists call eternal inflation. The inflating space keeps going. But in some places, inflation randomly stops. Those places where inflation stops become what we call bubble universes. They collapse inward into their own hot, dense beginning, their own Big Bang, and then expand and evolve on their own. Our universe might be one of those bubbles, and the inflating space around us, if eternal inflation is correct, just keeps going, producing more and more bubbles. Each one becomes its own universe. And because the inflating space keeps expanding forever, the number of bubble universes it produces is not just large, it is infinite. Now here's the extra twist. Each bubble universe does not necessarily have the same rules as ours. In our universe, the electron has a specific mass, gravity has a specific strength, the speed of light is what it is. But in a different bubble universe, one that formed under slightly different conditions, those numbers could be different. Some universes might have stronger gravity, some might have no electrons at all. Some might be completely dark with no atoms, no chemistry, no stars, no possibility of life. Most bubble universes, in fact, would probably be like this: empty, cold, or collapsing, or expanding so fast that nothing can form. But some, a tiny fraction, would happen to have the right conditions. And we should not be surprised to find ourselves in one of those, because a universe without the right conditions could not produce a person to notice that the conditions are wrong. We are here because we are in the bubble that worked. This is the level 2 multiverse. Other universes are out there, separated from us by inflating space we could never cross, each with potentially different laws, each equally real. Can we test this? Possibly. If bubble universes can sometimes collide, those collisions would leave faint marks on the oldest light in the universe, the cosmic microwave background. Scientists have looked for these marks. They have not found clear evidence yet, but future experiments might. The search is still going. Type 3. Every possibility really happens now we leave space entirely. We go into quantum mechanics. And this is where things get the most philosophically wild. Here is what quantum mechanics says. At the level of particles, electrons, photons, atoms, things do not have definite properties until you look at them. An electron, before you measure it, is not spinning up or spinning down. It is in a superposition, both at the same time. It is only when you measure it that it becomes one or the other. This sounds strange, and it is, but it is not a theory. It is directly observed. It is tested every day in laboratories around the world. Quantum mechanics is the most precisely confirmed theory in the history of science. And this weirdness, particles being in multiple states at once, is a real feature of reality. The question is what happens at the moment of measurement. How does both at once become one specific thing? The standard answer taught in most physics courses is something called wave function collapse. You measure the electron, the superposition collapses to one outcome, done. But here is the problem. The equation that governs quantum mechanics, the Schrödinger equation, never produces collapse. Collapse is just added on top of the theory as an extra rule. Nobody knows what causes it. Nobody knows what counts as a measurement. Nobody knows where the other possibility goes when the wave function collapses. In 1957, a physicist named Hugh Everett at Princeton looked at this problem and said something radical. What if there is no collapse? What if we just take the equation completely seriously? What does it actually say happens? The equation says both outcomes happen. The electron is spin up and spin down, both. The measuring device reads both outcomes, both. But then why do we only see one outcome when we look? Everett's answer, we also split. When you look at the electron, you become entangled with it. One version of you sees spin up, another version of you sees spin down. Both are real. Both are equally valid. The universe has not collapsed to one outcome. It has branched into two. And each branch contains a real conscious version of you, each convinced they saw the one true outcome. This is called the many worlds interpretation. And before you dismiss it, this is not fringe physics. This is taken seriously by some of the most respected physicists in the world. Sean Carroll at Johns Hopkins, David Deutsch at Oxford, Max Tegmark at MIT. And it happens not just when you look at an electron, it happens every time any quantum event occurs anywhere in the universe. Every radioactive atom that decays or does not decay, every photon that bounces or passes through, every quantum fluctuation in every atom and every star. Every single one of those events, right now, every second, is branching reality into more versions. The number of parallel realities implied by many worlds is so large that no number we have ever named comes close to capturing it. And every single one of those realities is as real as the one you are in right now. Can we detect other branches? No. By definition, once you are in a branch, the other branches have no effect on you. They are inaccessible, which is why many worlds is so controversial. Some physicists argue that if you can never test it, it is not science. Others argue that it is the most natural reading of the most successful theory in physics. The wave function does not collapse. It branches, and all the branches are real. Type 4. What if mathematics is reality? This one is the most philosophical. Bear with me, it is worth it. Here is a question that sounds simple. Why does our universe follow mathematical laws? We write equations that describe gravity. We write equations that describe how electrons behave. We write equations for the expansion of the universe. And these equations work beautifully. The match between mathematical prediction and physical reality is extraordinary. But why? But why? Why should the universe be describable by mathematics? Why not just random chaos? Why not something that follows no pattern whatsoever? One answer that some physicists take seriously is this: mathematics is not just a tool we use to describe the universe. Mathematics is the universe. Every consistent mathematical structure, every set of rules and equations that does not contradict itself, exists physically, not just on paper, actually exists out there somewhere as a real physical reality. Our universe is one mathematical structure, and there are infinitely many other mathematical structures, universes with completely different rules, different dimensions, different kinds of space and time, possibly so different from ours that we would not even recognize them as universes, all equally real. This is called the mathematical universe hypothesis. The physicist Max Tegmark, who has appeared several times already in this video, proposed it. It is the most speculative idea we have covered. There is no direct test for it, but it has a strange appeal. If everything that can mathematically exist does exist, then the question of why there is something rather than nothing has a simple answer. Because nothing, a truly empty existence with no mathematical structure at all, is the one thing that cannot exist. Everything else does. Type 5, the string theory multiverse, the last type, comes from string theory. String theory is the attempt to build one equation that explains everything: gravity, quantum mechanics, all the particles, all the forces, as different vibrations of tiny one-dimensional strings. We covered string theory briefly in the quantum field theory video. The key thing to know here is this: string theory requires extra dimensions, 10 or 11 of them, that are curled up too small to see. And there are many, many ways to curl up those extra dimensions. Each different way of curling them gives a different effective set of physics in the 4 dimensions we can see. Different particle masses, different force strengths, different cosmological constant. The number of different possible ways to configure those extra dimensions in string theory is estimated at 10 to the power of 500. That is 1 followed by 500 zeros. That is not just a large number. That number is so far beyond anything in everyday experience that the human brain cannot actually process how big it is. Each configuration is a possible universe. Combined with eternal inflation, which we covered in type 2, you get a picture where different bubble universes, as they form, each settle into a different string theory configuration. Different universes with different physics. All of them out there somewhere. An almost unlimited variety of realities. This is one of the most debated ideas in all of physics. Critics say that if string theory predicts 10 to the power of 500 different universes, it effectively predicts nothing, because any observation could be made consistent with the theory by pointing to one of the configurations that produces it. A theory that explains everything explains nothing. Supporters say this criticism is too harsh. The theory still has mathematical constraints. Not every universe is possible, only those consistent with the underlying string mathematics. And within that, the anthropic reasoning applies. We should expect to be in one of the rare configurations that allows complex life. The debate is ongoing. String theory has not been confirmed by experiment, but it remains the most mathematically rich framework physicists have for approaching a theory of everything. So is any of this real? Here is the honest answer. We do not know. We have not detected another universe. No confirmed signals from bubble collisions in the CMB. No observed branch of the quantum wave function. No window into the space beyond our cosmic horizon. What we have is this: our best theories, taken to their logical conclusions, all point toward the existence of other universes. Inflation points there. Quantum mechanics points there. String theory points there. Basic combinatorics about an infinite universe point there. These are not bad theories. Inflation is supported by extraordinary CMB data. Quantum mechanics is the most precisely tested theory in history. The combinatorics of an infinite universe follow from basic mathematics. The multiverse is what you get when you take our best physics seriously and follow it wherever it leads. Some of the most respected physicists in the world think this means the multiverse is real. Others, equally respected, think it means our theories need revision before we trust their most extreme implications. Both camps are serious people doing serious work. The question is genuinely open. What we can say is this: 100 years ago, the idea that the observable universe was just one galaxy, our Milky Way, seemed reasonable. Then we discovered it was one of hundreds of billions of galaxies. Each time we have thought we understood the scale of reality, reality turned out to be bigger. The multiverse might be the next step in that pattern, or it might not. But the fact that our equations keep pointing in that direction, 5 different types of theory from 5 completely different starting points, all ending up at the same answer, that is not nothing. The universe began 8 billion years ago. It has been expanding ever since. And somewhere out there, beyond any horizon we can reach, beyond any measurement we can make, there may be other beginnings, other expansions. other expansions, other histories, other yous, all real, all happening, all completely beyond our reach. And maybe that is the most extraordinary thing physics has ever told us. Not just that the universe is vast, but that the universe might be the least of it.